So the next topic that we will discuss in relation to Markov decision process is state value function. So this state value function we have already discussed in case of Markov reward process also. Similar definition will hold in Markov decision process. So in case of Markov decision process, the only difference that we have is that we have this pi as a subscript to the value function. So value function of a given state is nothing but it's an expected value of the total return that you will get for that particular state, and you are taking expectation of this gt, which is the random variable which we had already discussed in details in case of Markov reward process. The only difference now is that you have this value of a state for a given policy actually. So earlier this policy was not there in case of Markov reward process because there was no actions involved. Here in case of Markov decision process we have actions involved. So you will have value state function, value of any state depending upon the specific policy that you are following. So different policies will have different values for that particular state. So that's why it's policy dependent. And the question about why expected return and why can't we just compute the values of a state as a return straight away, this I have already discussed in case of Markov reward process. As we know that returns will be different for the different trajectories. We had taken a small example in case of Markov reward process. If you have not gone through my lectures on Markov reward process, you can go through it and check back again on this discussion. So because of the different trajectories giving you different returns, so it's a sort of random variable and we want to know the expected value of this random variable. That's why we are doing expectation. But still, to make it complete, I am just giving a small example to show that how actually the policy is acting a role in this calculation of the expectation value. So let's do that. So now we are considering a stochastic policy. In this stochastic policy, we are considering two actions. One is the down action, another one is the right action. So if an agent is moving down in a state, then its probability is 0.2. And if it is moving right, then its probability is 0.2. In the earlier case, it will be 0.8. So these are the policies that are defined for a particular stochastic environment. Here I am taking gamma as 1. So now if we take this as an environment, this is the grid environment and the agent is moving from point A and the final state is this I. So what we want is that our agent has to successfully reach this point I with the maximization of the reward. So here one of the paths that agent can follow is that agent will go down, then it will turn right, then it will go straight, and then again it will go down. So in these states where the agent is going, and in each of these states what will happen is, whenever it is making a transition from a possible state to a next possible state, it will get a reward of 2. Whereas if it goes from A to a non-prohibited state, which is given over here, it will be given a reward of -1. And similarly in these non-prohibited states, if the agent is moving, it will be given a reward of -1. So here in this particular trajectory, it has not moved in any of the prohibited states, so its rewards will be all +2. As you can see, +2 from moving from transition from A to D, and again +2, and again +2, and finally again +2. So once you have this reward in your hand, then the value function of this state A is given as 8. In the second possibility, it might be the case that the agent will move from A and it will take right. So if it takes right, then what will happen is, it will end up into a non-prohibited state. So this state is not allowed. It will end up into the prohibited state. So this is not allowed, as a result of which agent will be given a negative reward. So you can see here we have -1. But after that, once it moves to the right, once it moves down, this state is allowed, so it will be given a reward of +2. Similarly here, and similarly once it ends up into the final state, it will get a reward of 2. So finally you can see that based on the different trajectories, the value function that you will get for a particular state is different. So one is 8, another time it is 5. So because of this randomness is nature of the value function, we actually calculate the expectation of the returns that you are getting for a particular state. So this the answer for taking the expectation is clear from here. But now the important point is that you are actually following a policy in which the action, if you take in the action to be down, then that the probability of that is 0.8. But if you take the action to be at right, in a given state, then its probability is 0.2. So here you can see when the agent starts from state A, there is a 0.8 probability that it will go down and a 0.2 probability that it will go to the right. So you can see the arrows, I am making it of different length. So let me make it of different length. So this is actually the probability is 0.2 and the probability of going down is 0.8. So 0.8 arrow is more bigger than the 0.2 arrow, just to signify that the probabilities are different in both the directions. So what happens is, like, this particular path where it takes the action down, the chance of going through this path is 0.8, whereas the chance of going through this path is 0.2, because of the action that is involved at this state has a probability of 0.2. So because of this, what happens is you are actually multiplying these probabilities, that the ones which are coming from the from the policy itself is multiplied with the value function. So earlier when we had a deterministic policy, as it was in the case of Markov reward process, there was no actions involved. So at that time what was happening was these values were 1. But now, because the actions are involved and they are stochastic in nature, so they will be replaced by their corresponding probabilities. So that's why we are actually having 0.8 here multiplied with the value function of a particular state following that path, this trajectory, following this trajectory. The value that you were getting here was 8, right? So that's why. So finally, what answer you will get is 7.4. So something, if you observe here, it's important, that is the value functions, that these value functions are actually weighted by the policy that is governing that stochastic environment. So effectively what you are doing is you are actually doing this particular type of evaluation where your returns are actually multiplied by the probability of the action that is taken in a particular state S. So that's why the value that you get here is actually the value function following a particular policy. That's why V pi, the subscript pi, comes into play because of the multiplication of the return by this factor. So that's why there is a change in the terminology, and you have a pi in the subscript that denotes that your expectation will be depending upon the policy which you are following for that particular stochastic environment. So now, as we have understood how this value function is calculated for Markov decision process, which is actually it depends upon the policy pi. So let us draw the diagram for any state transition that happens in case of Markov decision process. So normally I will draw a very simple diagram. So what it has is it has two states. So you are moving from state S to S prime. So so in case of Markov decision process, you will have something like this. And what happens now is that instead of moving directly from S to S prime, there is a small intermediate small dot which we call as the action point. So let us say if it takes the action A1 based on the policy which we are following in this particular environment. So what happens is there will be a transition from S to A first, depending upon the policy that you are actually adopting in this particular state S. So once it takes this distribution value, that is the probability value, it moves to this action A1, and finally after that it will take this course to get to the state S prime. And the probability of doing this jumping actually is nothing but it's the probability of S prime and the reward that you are getting here depending upon the state and the action that you have taken. So this is the transition probability which actually comes after you move from action A1 to this S prime. So this is actually coming here. Similarly, if you take another path based on the policy, if you take another action, let us say you take A2 here, depending upon the policy, then what will happen is, this will be a2 by s, and then you will go here with the transition which is s prime comma r, given state and action a2, you will end up at state 2, let us say. This is state 1, let us say. So you are ending up in the futuristic states based on the intermediate probabilities that are happening in case of Markov decision process. Earlier there was no actions involved, so you are going straight away from here to state S1. And the important point here is that the rewards are actually jointly incorporated within this joint distribution. So that means, in case of Markov reward process, as I was telling you, there are no actions involved. So at that time you only had this probability with no actions involved here. So only this was the transition probability which was there. But now since the actions are involved, then you can easily visualize that somewhere this factor will be also playing its role in this transition probability. So if you look into the value function of the Markov decision process, you will realize that this thing is coming along with the original definition that we had in case of Markov reward process. Obviously this action terms were not there in that case, but now because actions are involved, so that's why these terms are appearing here again. So these terms which are appearing here are actually taken into account using this summation which we are putting at the outside stretch of the original definition of the Markov reward process, and this is coming because of the diagram that we are having over here. If you recall, this factor is playing its role. So somewhere what you are doing is you are actually, in order to calculate the expectation of this state, you are adding up all the values that you are getting over here at these nodes by the corresponding probabilities that you have for these values. So if you want to calculate the expectation here, you will do what? You will actually multiply this probability with the value that you obtained at this point plus the probability of this multiplied by the value that you obtained at this node, and likewise. So we will discuss the details of how we have derived this Bellman equation in our next lectures, but here I am just trying to give you the intuitive understanding that why summation is coming, because you are trying to find out the expectation of this node by taking contribution of all the actions in the vertical direction. So that's why you have expectation here. So now you can clearly see that we have the reward function, which is basically the function of S, A and S prime. So if you want to note down the reward function here, so it will be like this: S A2 S2, and this reward function will be denoted here as S A1 S1. So you can put the values of the reward at this node, and note that since the reward is a function of S, A2 and S2, that's why it will be here. Okay, so once this is done, you can have this as the value function calculation for MDP. So you can use this equation for calculating the value function. So this is also called as the Bellman equation for MDP. So now if you want to simplify this further, what you can do is, if you assume that R is independent of S prime, then what you can do is you can actually make this sum go inside, and since this particular term is independent of S prime, so what happens is only this term will be here and the summation can go inside onto this. And now what you can do is you can actually multiply this summation to both of these terms, so you will get this particular expression. And here what you observe is that now in the earlier case there was no this factor involved. In case of Markov reward process, it was only this factor, but now because only this factor with no actions, but now we have actions along with the factor which is over here. So that's why now it's R subscript pi, because the rewards are based on as per the policy. That's why we are denoting it by R pi. In the earlier case it was only R. In case of Markov reward process, it was only R. So now it is R pi, and this is as per the policy. Here we have V pi as per the policy, and then we have gamma times. This is the transition probability. As an overall probability, we are calling it as transition probability as per policy, and we are denoting it by P pi. And you can see here that now effective probabilities will be multiplication of this and this. So we take into account all these cascading probabilities to get to the another state, which is S here, S1 here from S. That's why you have this cascaded multiplication of the probabilities. So that's why we have this P pi. So effectively what is happening is, for a specific action, you are actually taking all the state transitions into account. So here if you see, there might be a chance that, this is a simplistic case, but I'll try to explain. There might be a chance that you will, go for multiple, states from this particular action itself. So effectively what you are doing is, for a single action, you are actually summing up all the transition probabilities. So that is what this particular expression is telling you, that for a single action, if you take from this set a single action, then you are summing up all the transition probabilities corresponding to that. So if you see here, this is what P pi is. That is, for a single action A1, you are actually summing up all the transition probabilities. So right now I am taking only single transition, so that's why it is S prime, but effectively it has to be pi A1 S. Then we will have all these summations, like all the summations means you will have first state reward, then state action A1, then S2 reward state action A1, like this. In the second action, if you take A2 by S, then again you can have multiple state transitions, action A2, then we can have S2 R state action A2, like this. So this is a generalized case which I am discussing over here, where the states can be up to n, but this equation actually consider only single state coming out from this action A1. So I hope you can understand what this P pi is now. So it's basically effective probability transition that you will calculate for this T diagram, which is a generalized probability tree diagram. So now P pi, I think you can clearly understand what that is. And similarly for the rewards, you can actually calculate for them easily by expanding these terms, where you have if you take a single action A1 corresponding to that policy, what is the reward that you are getting as A1, and then you can and you can expand it further. This particular mathematical expression which is given over here can be represented in terms of the matrix format as this, which is similar to what we have done for MRP. And from here you can simply do a matrix manipulation to calculate the value of V pi using matrix calculation. So let us do one small example on calculating this value function for the MDP in using Google Colab. But before going there, just wanted to tell you one thing, that if RS is independent of state S prime and A, then the above equation which is given over here, this equation, if the rewards are independent of actions also, then what will happen is your rewards also can be moved outside, and then you have summation on all the actions that you are taking in a particular state. And since it's a policy and you are taking summation on all the actions, so that value will come out to be 1. So you can reduce this particular expansion further to this. So this is basically also a simplified Bellman equation, and we will see in our next lecture how to derive these Bellman equations from scratch. But now what we will do is, we will actually calculate the value function of this equation using this equation for an example which we will take in case of Markov decision process. We will code it into Google Colab and see how we can get the value of V pi specific to a policy using Google Colab. So there is a slight correction to the earlier slide, which I wrote p pi as this thing. So there is a slight correction to this particular expression. So what exactly what exactly p pi is, that it's this particular expression times you have vs prime. So this is also there. So it was missing in the earlier thing. So this expansion is not valid anymore. It will not be the exact expansion. So we will change this in our coming slide. We will see what this expansion is. So, and also I'm dropping this p pi term here, so this will not be there in our next slide. This pi is not there, so I'm calling it as p here. So what is the intention behind understanding this expansion? The intention behind understanding this expansion is to understand how we can actually represent this double summation which is over here and over here in the form of matrix multiplication. So we want to see whether we can expand, whether we can expand this particular expression as a multiplication of two matrices, let us say A, B. So I want to see what this expression, what this matrix A is and what this matrix B is. And why we want to do a matrix thing, because we know that matrix multiplications are very fast compared to the normal summations, because here you see you have two for loops. One is this one, another one is this one. So cascaded for loops will take time in evaluating this expression. So it's better to convert this expression into a matrix format so that we can easily calculate all these values in one go by doing matrix multiplication. So that is our main intention for converting this expression into a matrix format. So let us see how we can do that. So here, if you see this expression I have written again, and now earlier it was not there, so now it is included. So now what you can do is you can see how we can expand this expression. So here if I take two actions, let us say, if I take multiple actions, let us say A1, A2, A3 till AN. So all these actions belongs to a set capital A. So what we can do is we can actually expand these terms. So what we will do is we will expand in terms of A1 first. So expand in terms of sigma first. So if you have A1 action, so A1 will be here, and then inside expression we will keep it same as this one. But the only difference is that this A will be replaced by A1 here, because you are actually currently considering A1 as the action. In the next summation you will have A2. And why this summation is coming? This is coming because of this summation which is here. So now this is the second action, and with that action you will have again an internal summation which is going on like this. And this will continue till you go for the last action, which is, let us say, pi an given the state s, and then you have a summation with all states and rewards, and then you have ps prime r and s comma a2, and then we have v pi s prime. So this is the final nth term. And one important thing I wanted to point out here is that in the earlier slides where we had discussed these expressions, please change this, like we have two summations here, s prime and r. Earlier this r was not there, so it was my mistake. So r will also be here along with this summation. So earlier it was only s prime, so please note that and correct it. So similarly here also r was not there, so please correct this. So now once we have this expansion ready in case of p, now the time has come to handle this internal summation, that how can we handle this internal summation, and can we represent it in the matrix format or not. And similarly for this expression, and similarly for the nth action expression. So now let us write for the single states. So here we will see the expansion for the different states. So s prime is again it belongs to a capital S. So s prime can be anything. It can be s1, s2 till sn, and it belongs to the bigger set capital S. So we are trying to expand this and see how we can express this summation. So here if you see, for a specific state s1, if you start, then you are taking this particular policy where in that state s1 you have this action a1 you have taken in that state s1, and then you have this summation which is going on, and Now this S will be replaced by S1. Earlier it was a generalized expression. If you see, this P is basically S here, so it's a generalized expression involving S. So when you are writing specifically some states like S1, S2, S3 here, then the changes that it will bring in is in this states S1. So if you write S1 here, so this is the change which will happen. And similarly, you can you can write for this expression. So it will continuously expand till the nth action, which is I am writing it in dots. So I'm not writing that nth expression, but it will be there. Similarly, now if you start from state S2, and then you can have multiple actions involved in that state S2. So you have action A1 happening over here. So this is the policy which you have for that state. And again, you can write these expressions which are internal to internal in the similar way. The only difference is that now it is S2 here. So you can do it till the nth state. Basically, what this is stating is, these policies are stating is that different states, how this particular action A1 is happening in that states. So this is basically the effective policy in which it tries to tell us that for different states, how this action is happening in that states A1. So A1 is the action. Similarly, this one here, it states that for different states, how A2 is behaving in these states. Look, what kind of actions you are trying to see in these states. So it is telling you that. So if we assume one thing here, so this is a very complex equation, so we want to actually simplify it further and see whether we can bring in some simplifications to these terms, and we want to write it into the matrix form. So that's why we assume something here. So the assumption is that the actions that we perform in all the states have same probability. So what it tries to say is that whether this action A1 is performed in S1 or this action A1 is performed in S2 or in Sn, all of them will have same probability alpha. So that is what we are trying to impose here in these equations. And what is the main intention of doing it? The main intention is to simplify these equations so that we can solve for the value function properly and fast. So if you have this action A1 having the probability alpha, then the action A2 which is valid for all these states will have a probability 1 minus alpha. So right now also I am considering only two actions, A1 and A2. I am not going for any other actions. So in that case you will have only these two terms, this one, and nth action will not be there because we have only two actions coming up here. So we are assuming that. So if two actions are considered, all the other terms will be 0. So now if we consider only two actions, these equations which are given over here will be reduced to a very reduced to this. So if you see here, all these all these probabilities that I am writing over here will have a single value of alpha, because what we have assumed is that this action A1 will be having the same probability in all these states. That is our assumption here for this particular problem. So if it is same, then it will have all probabilities value as alpha, and for this it will have all probabilities as 1 minus alpha. So this is a very simplification that we are trying to do here, specific for us for some problems. So if you do that, then you will have this thing. So this is the expression which we have here, and then we are writing this particular thing in a vector format as a single matrix. So we can write that over here. And similarly, this is for the second action, and all the terms are collected in the vector format like this. So now what we want to do is we want to actually replace this summation by matrix multiplication so that we can do it fast. That is our main intention, right? So in order to remove these summations and replace them by the corresponding matrix multiplications, we can do this thing. We will have this probability transition matrix, which we are denoting as P superscript A1 subscript S prime. And we have a vector which is V pi. So basically V pi is nothing but it's a one-dimensional vector, column vector, which is given like this. It has the value functions for all these states available. So if you take this matrix V pi here, and this is basically the state transition matrix, which we have already studied so many times. So this is the state transition matrix but the only difference between this matrix and the matrix that we had earlier is that the state transition matrix here will be specifically dependent upon the specific action which you are taking. So this state transition matrix will be written for a specific action A1. So it's a action dependent state transition matrix. Similarly, this one will also be the action dependent state transition matrix, and the action here is A2. And now we have V pi here. So now we can represent this complete P as a matrix P, which is basically the column vector containing all these elements. So now we have this expression in our hand. So now what we can do is we can actually collect the V pi terms in one side and collect the other terms on the other side. So if you do that, P is nothing but you are collecting V pi one side and you have kept the other terms on this side here. So now what we have is, this is basically the case where you have two actions, right? So if you want to generalize this for multiple actions, you can represent it in a general format like this. So this is basically a general representation. This is specifically for two actions. So, and this plus is basically representing this summation over here. So you can see that and what this alpha is nothing but it's a policy. Actually, if you recall, it's a policy in which you are saying that what action you are taking in that specific state and what is the probability of that. So it's a policy actually. So if you see this particular expression, you can easily recognize that this particular thing is basically a policy dependent state transition. So all the actions that you are taking, the transition matrix that you are creating is based on the actions that you are taking in that state. So it's a policy dependent state transition matrix, and it's not the normal one, as I have already notified here in explaining it, and I have written it here also that this PA1 S1 is the state transition matrix under action A1, and this is the state transition matrix under action A2. So this is basically a policy driven state transition matrix. It's not a normal state transition matrix which we have in our earlier lectures. So what we do is, in order to distinguish this thing from the normal state transition matrix, what we do is we represent it like this. So you can see in the superscript I am writing pi. So if I am writing pi over here, that means it's a policy driven state transition matrix, and policy is somewhere deciding the actions which are coming over here. So based on different actions A1 and A2 which are defined by the policies, you have different state transition matrices. So we can represent P as the multiplication of these two matrices, which is given over here. So multiplication of these two matrices tries to implement this particular expression which is over here. So you can see earlier we started out by saying that we will represent this by a multiplication of two matrices A and B. So A is nothing but the state transition matrix P pi, and B is the vector V. So if we multiply these two matrices, we will get this implementation of double summation in the matrix format. So this is basically the expression for P. Now if you recall, the second expression that we have is R pi, and this R pi is nothing but the reward matrix which we have here. I'll just recall that. So this R pi is nothing but the summation of the pi as times RSA, and this is coming from this expression. So our objective is to basically represent the matrix representation of this equation so that we can calculate the value functions of these states in a very fast and efficient way through matrix multiplication. So this is our objective, right? So now we have done it with this one, and you can recall that our values are gamma, v pi, p pi. So now here it's not here, it's pi here. So please bear with me with the terminologies. I will change these definitions in the coming slide, but to be precise, we are trying to represent these equations which are very complex in the form of matrix. That is our main intention of doing this. So now continuing with this discussion, you can see that if you expand this expansion for different states, like if I'll take R pi S1, so in that only S1 will change here, and then S1 will change here, and then we have these actions. So if I take actions A1, A2 till AN, so you can expand these terms like this. Similarly, you can go for the nth term expansion also like this. And now what is our job? Our job is to simplify these equations so that we can represent it in the matrix format. And with our assumption, which we had already told earlier that the action A1 for all these states will follow the same probability alpha, and similarly action A2 in all these states will follow the probability 1 minus alpha. So if you do that, you can actually write all these terms with a single term alpha, and then you can represent this as a matrix format, this thing. So you can represent this equation which is on the top here in the matrix format like this. So this is similar to what we had done earlier in case of probabilities. So this is, we are doing it for the rewards. So now again the important concept here is that this or one dimensional column vector is basically nothing but it's the rewards that you get for the state for a specific action that you are taking. And similarly, this is basically the rewards for all these states for a specific action A2. So you have to actually create these matrices separately for different actions. So rewards will be calculated for different actions separately, and then they will be weighted by the policy factor which is given over here. So it will be multiplied by alpha and 1 minus alpha. And somewhere you can, write this in generalized expressions like this, where this summation is basically for all the actions. In this case, we are taking only 2 actions, but if it is an nth, if there are n actions, then this summation will be represented by this summation, which is a generalized one. And then you have this. So basically, this is nothing but, this thing is basically nothing but it's a reward under a policy pi. So this is basically a reward that you will, collect for different states, but governed by the policy pi. So that's why we have, this thing over here. Forgive me for different, conventions over here. So it will be like this to be specific. And so once you have this as a matrix representation, so please recall this is the matrix version, matrix representation, which is given over here. So you can have, these as the matrix, you can calculate for different actions and then you weight it. So finally you will have a matrix representation which is given like this, times this one we have already derived earlier. So here this gamma is the discount factor, and once you do the matrix multiplication, the value of v pi will come out to be this. So this is the matrix representation of the Bellman equation for the MDP which we had which we were targeting, and by using this you can easily calculate the value functions for all these states. So this finishes off with the representation, that how to represent Bellman equation using matrix. In the next slide, what we will do is we will actually discuss one small example to further enhance our knowledge to how to write these equations and how to write these equations which are given over here, so that we can calculate the value function for a specific problem. And then after that we will discuss a simple example using Google Colab, how to calculate these value functions. Once this is done, then we will move to next chapter where we will derive these Bellman equations from scratch. So we will not assume any information here like the one which I have given over here, right? I have directly given you this expression, so we will not assume anything. We will derive from scratch how we are getting this value function in the MDP.